I'm not.
Calling from.
I'm kind of thank you.
Oh. Okay. It's weird. Hello, can you hear me? Yeah, definitely you can hear me. Yeah, I just want to ask about the people in the Zoom. Sorry. Yeah. Great. Thank you. Laura? Okay. Thank you, Angela. Okay. So, okay. We will start.
You read this book. Where's your link?
Okay, hi everyone. Howdy. So yeah, so there are two announcements before the starting the lecture. So first announcement is that actually there are some people who cannot access the recorded lecture in the Zoom. I don't know why. So I just work with some IT help center, and they also can access my video, but I'm not sure some of the students cannot access the video. So I will upload it on YouTube, and you can watch it on YouTube using the link I sent. So I will send the link after the class. So you can freely use the link, but please do not share with anyone else because actually the copyright of this lecture is not on me, but not on you, but it's on the Texas A&M University. So it makes them rich, but anyway, so it cannot be allowed to share the class video without permission from the provost. So just use your own watch, right? Right? Please do not share the link. So that's one announcement. And for the second announcement, yeah, as I said earlier, we will have a quiz. So I will just let you show how to do the quiz, for example. So first of all, you need to do the test quiz. So to do this, first of all, just go to, sorry, WebAssign, then maybe you can see this kind of screen. Then please click the test quiz. Then there will be assignment restriction. So first one is you must use the WebAssign lockdown browser for this assignment. So click this lockdown browser here. Then you can see this link. So please test lockdown browser installation. Yeah. Oh, sorry. Yeah, I need to share the screen. Sorry, thank you very much. Give me a second. I will share the screen. Okay. Oh yeah, so I will do it again. So give me a second. So yeah, in the starter, if you just log into the WebAssign, then you can see this kind of screen. Then please click the test quiz. Then you can see this lockdown browser required, password protected, and timed assignments. So then just click the lockdown browser here. Then you can see some, a bunch of writings, and there is some button, test lockdown browser installation. So depending on your program, depending on your computer, so if your computer uses Windows, then just click Windows. If your computer uses macOS, then you can just download the macOS file. So anyone is okay. So give me a second. So I just downloading the lockdown version. So it will take some time to do that. So, and the password for this test is test. So this is for test quiz, and I will send the password for quiz 1 after the lecture. So you can take it home. You can take the quiz after the going to home, right? So, and the original, so this test quiz takes 2 minutes. And if some of you already take the test quiz, then maybe it is less than 2 minutes, right? Because the answer of the test is 1. I already said. And actually the problem is just writing down 1 in your test, then you're fine. So test quiz have only 1 problem. And for the quiz 1, there are 9 problems, but it doesn't mean that you have 9 different of graphs and solve it everything on 10 minutes. Instead, there are only 1 graph, and it questions about 9 properties of that graph. For example, how many vertices are there? How many edges are there? Are there any Euler paths or circuit? How can you Eulerize the graph or something like that, right? So I don't think that 10 minutes is short for the kids. So I think that it is enough for kids, but just let me know if all of you think that it is very difficult to solve it for 10 minutes, then I will extend the time next quiz, or I will just do some coordination on that, right? So the quiz, you can start the quiz after this lecture, and you can just solve it today before the 12 a.m. of today. What I mean 12 a.m. is just midnight, then you can solve it. So as you see, if you just click to solve it, then it already, after 10 minutes, you can solve it more, right? So it means that if you just click to start the test, then you need to solve it in 10 minutes after the click, right? So okay. So, okay, now we downloaded this browser. Oh, okay, this computer needs admin privilege. So, okay, then I'm not an admin. So, okay, but I think that it will work for your computer. So yeah, so just install your lockdown browser, then just click this launch lockdown browser button. Then it will automatically start your lockdown browser on your computer. Then you can take the quiz, right? So if you have any question, okay. Pardon? What if couldn't? Oh yeah, if you're not able to take quiz, then just email me, please, right? If you have any technical difficulty on the taking quiz, just email me directly, then I will find some solution for you. Maybe, yeah, maybe there are some other ways of taking quiz, like using other browser or using other computer, or in the last case, using the just paper quiz, but that's what I want to avoid because that's not, that's against the university's policy that having the same environment for everyone. So, but anyway, so we will find a way. So if you have any technical difficulty, please let me know. Yes. A password for the assignment. So in this one, this test one is just TEST, test. And the password for quiz one, which will be announced later, I will email you after this lecture. Okay. Great. And do you have any other question? Okay. Okay, so yes, I think that everybody, including me, had a difficult time to deal with technical difficulty, but please let me know so that we can deal with it together, right? And the last announcement is that actually I've got some complaint about the WebAssign homework program, especially number 8, that they represent some graph, but it's related to wrong answer, or someone just got every just got every problem correct, but they do not get a full credit on the WebAssign. So in that case, please report your cases and with a screenshot with email. Then I will take it into account on your homework grade, right? So if you have any problem on WebAssign, then just report it to me so that I can see what you're doing and maybe I can handle it, right? Do you have any other question? Great. Yes, then let's start the lecture. Okay. So, okay. So today we will deal with the chapter 2, and chapter 2 starts with the Hamiltonian circuit or Hamiltonian path. So I just want to recall you that the Euler path or Euler circuit is the path or circuit containing every edges in the graph at once, right? Containing every edges in the once. So, and there are some questions from the Zoom, so let's check it. Oh yes, so Alexis, as I said it earlier, so I will upload my lectures on YouTube. So I will give you some link for YouTube links so that you can access it after this lecture. So, sorry. Thank you. Okay. So Euler path and circuit is just some path and circuit containing all edges at once, right? So the Hamiltonian path is containing all vertices at once, right? Or Hamiltonian circuit is a circuit containing all vertices at once, right? So it doesn't require you to have all edges, right? Instead, it requires you to have just visit all vertices at once, right? So that's the Hamiltonian path and Hamiltonian circuit, right? Okay, so let's deal with some examples. So first of all, first example we can deal with is just this graph. So it seems a little bit complicated, but just try to find the circuit or path containing every vertices at once. So maybe start with A, then traditionally I just go to B, and then, yeah, then go to C, go to D, E, F, G, and go back to A, right? So it is one of the circuit. So it contains every vertices at once, right? So this Hamiltonian circuit is A, B, C, D, E, F, G, A. So it contains every vertex. Okay, question? Yes, so it is except the beginning point. Sorry, yeah, that's what I did incorrectly. So in case of circuit, yeah, definitely we need the starting point we need it twice. So, but that's a good point. Thank you very much. Yeah. So what she said, what are your name? Yeah, what Harry says is that a circuit should have the starting point twice, right? So it is a little bit, different with the original definition of Hamilton path. So we just didn't think it as a kind of exception for definition of Hamilton path, Hamilton circuit, right? So in case of Hamilton circuit, starting point is only counted twice, but all other vertices only counted once, right? So that's the Hamiltonian circuit. Good point. So in this case, Hamiltonian circuit exists. And also Hamiltonian path but not a circuit also exists, right? So it is just nothing but you can just delete the last point A, right? A, B, C, D, E, F, G. Then it is just path because we do not go back to A again. So, and we still Hamiltonian, right? So both Hamiltonian circuit and Hamiltonian path exist. And there are so many other Hamiltonian passages exist, right? Or circuits. For example, you can just go to A, B, C, E, D, F, G, right? So some other ways. So, yeah, so Hamiltonian is vertices, not edge, right? So well, we ignore DF and CE, at least in this circuit, right? Because Hamiltonian circuit do not need to include all the edges, right? Great. Do you have any question? Okay, great. Then let's deal with one more example. So this example, again, we can start with A. Then maybe you can have a Hamiltonian path by going a Hamiltonian circuit by A, B, D, C, A, right? So that's one of the Hamiltonian circuit. Or you can go to, how can we? Yeah, I think that's the only Hamiltonian circuit. And however, there are one other Hamiltonian path. Can you figure out what is the one Hamiltonian path, which is not in the circuit, using the diagonal line? So can you find the Hamiltonian path which contains the diagonal line, but not a circuit, but containing every vertices? Yeah, maybe take out the last is one of the options. And is there any other paths? ACBD, great, yes, ACBD, right? Because, what is your name? Kayhan? Thank you. As Kayhan said, ACBD is also Hamiltonian path because it contains every vertices at once, but it is not a Hamiltonian circuit, right? Because B is not the same as A. And yes, and as Rockney in the Zoom says that ABCD is also a Hamiltonian path because ABCD is also just containing all vertices at once, but it doesn't contain, it doesn't go back to A again, right? So great. Okay. Do you have any question on this example? great. And let's do it one more thing. So in this example, can you find the Hamiltonian circuit or Hamiltonian path for this third graph? No. Why? Yes, it's a little bit difficult to get everyone once because, for example, if you just want to start with A, then maybe you can just include A, B, C, and D. But after D, you need to choose go to E or go to F, right? But when you just go to E, then you need to go back to D again to get to F, or vice versa, right? So in this case, neither not exist and do not exist, right? Okay. Not exist. Sorry. And it's also do not exist. So, and the next example, maybe you can find the Hamiltonian path. For example, you can go A, B, C, D, F, E, or E, F, right? Or you can go A, B, C, D, E, F, right? So it is Hamiltonian path, D, E, F, or A, B. My God. Oh, yeah. So
Hey, we can't hear you at all anymore. We didn't mean for you to mic it. There was a student who didn't have the mute mic and we couldn't hear you, so but we can't hear you teach anymore.
okay, can you hear me?
Yes, thank you.
It's a little bit echo, so I don't know. I can deal with it. Give me a second. Yeah.
Sorry, the reason we were typing that was because one of the other students had their mic on.
Ah, okay, got it. So, here. Oh. So, okay. So sorry for this echo. I will Okay, sorry for echo. Okay. Okay, now it's good. Okay. Sorry for echo. But yeah, so because my mic has, I think their powers are off, so my previous lecturer do not put it in the right way, so they use this mic instead of it. So sorry about this echo. So yeah, so in this case, there are no Hamiltonian circuits because again, if you wanna go back to A from E, you need to get D or C, right? You need to go to D or C again because there are no way to directly go E without taking C or D. So in this case, they do not exist, right? Okay, do you have any other question? Pardon? Oh. Speaker? Uh-huh. Oh, it works. Okay. Thank you. So can you hear me in the Zoom?
Yes, that's much better.
Okay, got it. Thank you very much. Yeah, thank you. Yes. Okay, great. So yes, so next one is just, yeah, actually if we find the Hamiltonian path, we will just use the, just rule of thumb, right? Just try to draw some graph and find the Hamiltonian circuit. But there are some better way, some systematic way to finding the Hamiltonian circuit. And we will say that it is tree method. So actually tree method or method of tree is, yeah, have there a lot of several steps. But instead of, remembering or drawing it, yeah, if you just see what I did, then you can see what the method is. So tree method is nothing but just make a tree for each vertex. So for example, start with vertex A, then you can just draw your vertex A in here. Then now all you can do, or all you can go from A is just E or C or B, right? So just draw these edges. Then when you from A to go to E, then all you can go without going to A is F or D, right? So just draw F or D. And if you just go to C from A, then all you can go is D or B, because you didn't want to go back to A again without taking our other vertices. And if you just go to B, then all you can go is just C, right? Again, if you just use A, E, F, then all you can go is just D, right? Because you already go to E and you already go to A. So from F, there are only 2 points you can go, E or D. And if you are in D, then you can go to C or F, right? Because we didn't use C or we didn't use F. And if you are in here, D, if you just follow the A, C, D, then you can go to E or F, right? And if you are in B, if you go to C and B, then all you need to go back is just A, right? But you know that this is not a Hamiltonian circuit, right? Because it just go back to A without taking E, D, F in each circuit, right? So it is not Hamiltonian circuit. So we don't need to figure it again. And if you just go back to C, A, B, C, then the point you can go is D, right? Then, okay, now, yes, I like this question that is that because B already goes to A and shouldn't need it to be repeated? Yes, you're right. Because, yeah, this ACBA, if you just try to go ACBA, then, yeah, it already has a circuit, so it repeats A twice, but it didn't count E, F, D on each path, each circuit, right? So that's why we can see that ACBA is not Hamiltonian circuit, right? Does it answer your question, Alex? Okay. So ACBA is not considered as, yeah, in case of Euler circuit, then maybe you can use. So in case of when you're making Euler circuit, then maybe ACBA can be allowed. But in case of Hamiltonian circuit, it is not allowed, right? Because it counts the point A twice, right? Got it. Then, okay, thank you. Then let's try to deal with again. So when you choose A, E, F, D, then all you can go is just C. And when you go to A, E, D, C, then all you can go is just B. And when you go to A, E, D, F, then again, all you can go is just E, right? But in this case, still you have two E's in one circuit, so it is also not Hamiltonian circuit, right? And in case A, when you goes to A, C, D, E, then all you can go is just F. And when you can go A, C, D, F, then the remaining one is just E. And when you go A, B, C, D, then maybe you can go E or F, right? Then again, when you go A, E, F, D, C, then the remaining one is just B, right? And when you go A, E, D, C, B, A, E, D, C, B, again, you need to go back to A, but in this case, it is not Hamiltonian circuit because F is missing, right? So, not Hamiltonian circuit because F is missed. And when you're just taking A, C, D, E, F, A, C, D, E, F, again, it is not Hamiltonian circuit because there are no way to go back to taking B instead of taking D or E, right? And when you just go to A, C, D, F, E, then again, you need to go back to A, but it doesn't take B, so it is not a Hamiltonian circuit. So, and lastly, A, B, C, D, E, B, C, D, E, then it goes to F, and A, B, C, D, F, A, B, C, D, F, then you go back to E. So there are only three possible cases are here. So the first case, when you just go to A, E, F, D, C, B, then you can go back to A, right? So it is Hamiltonian circuit. So this one is Hamiltonian circuit. And in case of A, B, C, D, E, F, A, B, C, D, E, F, then there are no other points to go. So, but it contains all points in the graph, right? So it is Hamiltonian path. But not a circuit, right? And lastly, when you do A, B, C, D, F, E, then you can go back to A again. Then it contains all F points. So it is Hamiltonian circuit. Right? So there are two possible Hamiltonian circuits and one Hamiltonian path, but not Hamiltonian circuit. So that's the tree method. So what you need to do is just choose the first point and draw it, and just choose the other next point you can go to from the first point using an edge and just writing it. Then just writing it again and figure out whether it is Hamiltonian path or not for each time, right? Then you can find all the passes, whether it is Hamiltonian path or not, right? Okay. Do you have any question? Could you repeat again? Oh, that's good point. So what is your name? As Romsado said, yes, actually, if you just find one circuit, then you can just find the other circuit by pre-picking one, right? So for example, actually, yeah, this circuit A, B, C, D, F, E is actually pre-picking of the circuit A, E, F, D, C, B, right? So actually, if you just find one Hamiltonian circuit, then you can find another by pre-picking it once, right? So always Hamiltonian circuits have is even number. There are even number of Hamiltonian circuits for each graph. Okay, question? Mm-hmm. Yes, you're right. That's also a good point. Oh, Haley, yeah. Yeah, so what Haley's question is that actually if we start with another point instead of A, maybe you can start with the point C, then Haley's question is that can we find the Hamiltonian circuit with the other one? And my answer is that, yeah, it doesn't matter which point you start. So maybe, yeah, if you just start with other point, then you can find the Hamiltonian passes or circuits, but it is still the same as Hamiltonian paths or circuits you can find in this tree method for A, right? So in case of Hamiltonian circuit, yeah, it doesn't matter for your starting point. However, so in case of Hamiltonian paths, actually it matters. For example, if you start with D, then maybe you cannot find the Hamiltonian path, which is called A, B, C, D, E, F, because in case, yeah, D is the middle point, so you cannot go back to it without using it. So you can find a little bit different path. But in case of Hamiltonian circuits, you can always find Hamiltonian circuits for no matter what whether your starting point is, right? Okay, but that's a good question, Harry. Okay, so I will mention it here. Yeah. So Hamiltonian circuits the same no matter what your starting point is. However, Hamiltonian paths may be different or maybe not be found. Yeah, that's a good point. And actually, it is actually the level of the upper division course. But thank you, very good question. So thank you very much. Okay, do you have any other question on this method of tree? Okay, great. So let's try to find some more Hamiltonian passes. So especially since it is a business mathematics course, so we are actually interested in the optimal Hamiltonian circuit. So in one of the optimal is that maybe kind of the Hamiltonian circuit with minimum weight or minimum distance or something like that, right? So an optimal Hamiltonian circuit is the circuit that has the least weight among all Hamiltonian circuits, right? So for example, maybe we can deal with this using this example. So as you can see, there are some maps, and each maps and each edges actually has a rank, which is the cost, which is just travel time in hours. So for example, if you just want to go to Belize from the Miami, then you will take 2 hours to get to there, right? Maybe it is about the airplane, but anyway. So there will be some graph. And I want to find the Hamiltonian path of this graph, right? Sorry, Hamiltonian circuit of this graph with the optimal one, which means that the least weight Hamiltonian circuit. So to find this, okay, so my starting point is we need to merge start and end in Miami. Then say just starting point is M. Oh, sorry. And there are 3 choices possible. So first of all, you can go to Belize first, or you can go to San Juan first next, or you can go to Barbados, right? So in each case, when you go to Belize, you need to take 2 hours to get to there. And when you go to San Juan, you need to have 3.5 hours. And for Barbados, you need 4 hours to get to there. And when you go to Belize, there are 2 choices. Maybe you can go to San Juan, or you can go to Barbados. So in any case, it takes 6 hours, and in case of Barbados, it is 8 hours. And when you go to San Juan, maybe you can go to Belize or Barbados. Oh, okay. I need to write down Belize for Belize and Barbados for B, so to distinguish them. So in that case, it is 6 hours, or Barbados is 3 hours. And when you go to Barbados, again, you have 2 choices. You can go to San Juan, or you can go to Belize. And in case of San Juan, it is 3 hours, and Belize, 8 hours. And the last choice is you already go to Belize and San Juan, so the remaining one is Barbados, and remaining one is San Juan, and remaining one is, for the third one is Barbados and Belize, and Belize, and San Juan, and SJ to B. Barbados is 3 hours. Barbados to San Juan is also 3 hours. And Belize to Barbados is 8 hours. Barbados to Belize is 8 hours. And San Juan to Belize is 6 hours, right? Then lastly, since we want to find the circuit, so you all need to go back to Miami again, right? So in that case, sorry. So from Barbados to Miami, you need to have 4 hours. And from San Juan to Miami, it takes 3.5 hours. And from Belize to Miami, it takes 2 hours, right? So yeah, so there are 6 possible circuits you can have, starting from Miami and ending at Miami, right? So in that case, you can just add all the possible edges. So the first one takes time 2 plus 6 plus 3 plus 4. And the second one takes time 2 plus 8 plus 3 plus 3.5. And the third root takes time 3.5 plus 6 plus 8 plus 4. And the fourth root takes time 3.5 plus 3 plus 8 plus 2. And 5, the fifth root takes 4 plus 3 plus 6 plus 2. And the last root takes time 4 plus 8 plus 6 plus 3.5. So the first one gives you 15 hours, and the second one gives you 16.5 hours, and third one gives you 21.5 hours, and 16.5 hours, and 15 hours, and lastly, 21.5 hours. So as you can see, the root 1 or root 5 is the optimal one, right? Because it takes the least time among all possible Hamiltonian circuits. Okay. Do you have any question? This. So yeah, so in this example, all you need to do is just finding Hamiltonian circuit as much as possible using the method of tree, then just adding all the weights in the circuit to find the least weight circuit among all possible Hamiltonian circuits, right? So maybe finding the weight of circuit is a little bit difficult, but it is just nothing but summing all the weights on the edge. So yeah, that you can find it, right? Okay, so in this case, the answer is from Miami to Belize to San Juan to Barbados and go back to Miami. Or again, you can just go in the other way, right? So one of these two circuits will be the optimal Hamiltonian circuit, right? And as Lob said about this, so always Hamiltonian circuit has the another circuit which is just go back around, right? Great. Okay. Do you have any question? Good. Great. Yes. Okay. So, and let's deal with some graph question. So, okay. So, and as you see in this example, actually, yeah, in this example, there are no failure case, right? So every 3 cases actually gives us some Hamiltonian circuit, right? So this is very special case. Usually it is not happen on the usual graph. So in this case happened only when your graph is a complete graph. So that's what I want to explain right now. So a complete graph is a graph which every pair of vertices is connected by exactly one edges, right? It means that if you just pick 2 points in your graph, then for any of these pair of points, you have an edge between them, right? So that's the called complete graph. So for example, this first example is case of complete graph because there are 2 vertices, and these 2 vertices, you have 1 edges between them, right? So it is complete graph, and it has 2 vertices and 1 edges, right? Is it good? Okay, great. And the next one, is it a complete graph? No, why? You're right. What did you name? Carly? Catherine, sorry. Yeah, as Catherine says, it has 2 edges between this pair of vertices, right? So it is not a complete graph, right? So in this case, number of vertices are 3, but number of edges are 4, right? Okay. And the next case, is it complete or not? It is complete, right? Because for every 2 edges or every 2 vertices, you can find an edges. So it is a complete graph. And it has 4 vertices and edges are 1, 2, 3, 4, 5, 6. 6 edges, right? Now compare this graph with rectangular with diagonal with this graph, right? Can you see that they are similar? So the graph in the map looks like this, right? So it looks like this. And our map, our complete graph in the below example looks like this, right? So can you see that those are similar? So maybe if you just move your edge in this red edge to inside of the middle of the rectangular, then you can see that actually they are very similar, right? So even if their shape is not the same, but both are actually complete graph with 4 vertices, right? Does it make sense? Okay, great. Yes. And the next example looks like there is star among the 5 points. So is it complete or not? Yes, right? Is it complete, right? Because you can find any edges between one or any 2 of the vertices. And the number of edges are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? There are 10 edges. And the next example, so it has still 5 vertices, right? Is it complete or not? No, right? Because in this case, you cannot find an edge between these red points, right? There is no edges between them. So it is not a complete graph. So in this case, each number of vertices are 5, but number of edges are 4, 5, 6, 7, 8, right? So Alex's question that why is your curved line not seen as a complete graph? Oh, so no, in this case, curved line is not a problem. The problem is when you just taking these two red points, for example, like A, B, then there are no edges between A, B, right? But if you just remember the definition of a complete graph, then complete graph is a graph which every pair of vertices is connected by exactly one edges, right? But AB is not connected by an edges, so that's why we can say that the last example is not a complete. Does it make sense? Great, thank you. Okay, do you have any other question? And Morgan questioned it that would it also be incomplete because there are two lines connecting two vertices? Yes. Yeah, that's what Alexis said. Okay, yeah. Yes, because, yeah, okay, so for example, say this point is C, then AC has two edges, right? So it also makes this graph not complete, right? Because we only allow one edge to be complete, right? Okay, that's a good point. Thank you, Morgan. Great. And is there any other question? Wow. Thank you very much. Yeah, actually, yeah, I didn't find it when I prepared this lecture, so you guys are very talented. Thank you very much. Great, yes. So, okay, next example is example 1.9. So draw a complete graph with 3 vertices, and we want to find all possible Hamiltonian circuits, right? So first of all, we need to draw 3 points. Then to find the complete graph, we need to connect every 2 pair of vertices by an edge and edge, right? Then it is triangle, right? And there are no edges we need to add. So the complete graph of 3 vertices is not just nothing but triangle. And just naming A, B, C, then we can find all possible Hamiltonian circuits. So first circuit is maybe A, B, C, A, and the other circuit is just flipping it around. So it is A, C, B, A, right? And you can just define another circuit by, just moving around this one. So for example, if you just using this circuit ABCA, then you can find BCAB, right? It is actually the same circuit. And again, you can find CABC, right? So it is just the same circuit. Likewise, from ACBA, you can find CBA, ACBA, CBAC, and BACB, right? So it is just circulating the letters to find another Hamiltonian circuit. So these are actually, it seems the different circuit because the starting point is the different, but actually they are the same circuit, right? Because it is just in the circuit, any starting point is just give you the same course, same one circulation, right? So these are all possible Hamiltonian circuits, right? Okay. Do you have any question? This example? Great. Okay. And again, I want to just emphasize that the number of vertices is 3 and edge is just 3, right? So actually, Rainy questions that would you have to list out just the beginning 2 or 6 because they are the same circuit, and it depends on the problems. But yeah, in this textbook, they think it as a different one because starting point of circuit is different. So when you have some question about this kind of circuit in RebaSign, then please name all other all 6 circuits as your Hamiltonian circuit, right? So, but yeah, in usual discrete mathematics, it is actually counted as your same circuit. So, but in this textbook, they regard it with different ones. So that's why I named all these parts of the 6 circuits, right? So thank you very much, Rainy, for pointing out. Okay. And the last 3 are not last. Yeah. So, and from here, what I want to say is that, so say thinking about the complete graph, with vertex 2 has 1 edges, right? And complete graph with vertex 3 has 3 edges, and complete graph with 4 vertex has 6 edges, and complete graph with 5 vertex has 10 edges, right? So there are some relationship between the number of vertices and number of edges between complete graph, right? So for example, so thinking about to count all the edges, for example, in the complete graph of the 5 vertices, first of all, you can choose point 1, right? Then for each point, you have 4 edges, right? And there are 5 ways to choose your edges. And there are 5 minus 1 edges for each point, right? But you can do it for each 5 vertices, right? Then for example, if you just count it using this edges using this point, say A, then you can count it again using B as your starting point and A as the ending point, right? So we need to remove it that cases. So we need to divide it by 2. Then it gives you 5 times 4 over 2, which is 10, right? So the number of edges, so in case of m vertices, the number of edges are m times m minus 1 over 2. And in this case, n is number of possible choices over vertex. And m minus 1 is number of possible edges from the chosen vertex. And 1 over 2 is just delete the thing. For example, edge AB is the same as edge BA, right? So these are the meaning of this n, m minus 1, and 2. I know that this is a difficult point, so if you have any question, please let me know. It seems a little bit tricky. Is it good? Great. Pardon? Could you repeat again? Formula, yes. So in this case, my formula is that the E is v times v minus 1 over 2. That's what I use. And in this case, yeah, I just explain how can I get this formula from nothing, right? So that's the formula. Do you have any other question? So actually this formula is can be written in the question in the below page. So how many edges does your complete graph with n vertices have? So it is n times n minus 1 over 2. And you can explain why the formula holds because this n is, as I said earlier, it is number of choices of vertex. And this n minus 1 is of choices of edges from the chosen vertex. And this half is just delete repeated edges, right? So that's the meaning of the formula. And actually it is related to fundamental theorem of counting, right? So it is just, so you have k tasks to be performed. So for example, you have 2 tasks to be performed. So for example, you can do quiz 1 and you can do quiz 2. And the first task can be completed in n ways. For example, the first task 1, can be completed in the 3 ways. And the second task can be completed in the 2 ways. And then the total number of ways you can complete the task is 3 times 2 is 6, right? Does it make sense? Because, okay, how can I explain it this? So it's like choosing a sandwich from the Subway, right? So when you go to Subway to buy a sandwich and they ask you what kind of bread do you want? And there are maybe 6 kind of bread in Subway here, right? And if you just choose one of the bread, for example, I like the white bread, so I just choose white bread. Then they also question you, what kind of meat do you want? So maybe they have chicken, poultry, or beef. So maybe they have 3 cases of bread, 3 cases of the meat. So okay, so bread, you have 6 choices of bread, and for me, 3 choices of meat. And for vegetables, there are plenty of choices, maybe 10 choices of vegetable. Then all you can eat on the Subway sandwich is just 6 times 3 times 10, which is 112 ways to get the sandwich from the Subway, right? So almost 1/3 of your year, you can just take the different sandwiches from the Subways, right? So that's just called fundamental theorem of counting. So if you have choices for one thing and the other thing and the other thing, then all possible choices you can have is just multiplying every choice, right? So that's the theorem of counting. Does it make sense? Good. So, okay. I'm not sure that, yeah, it is not advertisement. It is just example for doing something, buying some sandwich from some shop spot. Anyway, yes, so yeah, this. So in the case of CRM, so if you have K tasks and first task can be completed in N1 way, second one completed in N2 ways, and I's task can be completed in NI ways, then total number of ways of that this K task can be performed is N1 times, N2 times, N3 times, so on, and Nk time, Nk, right? So this is the total number of ways you can do it some task by choosing, yeah, the ways, right? Do you have any question? Mm-hmm. Oh, thank you. Kate, thank you, Kate. Yeah, 6 times 3 is 18, so it should be 180. Thank you very much, Catherine. So I'm not good at, calculation. So anyway, great. Yeah. So it is 8. Right. So let's deal with some examples. So how many outfits can be made from 2 shirts and 5 pair of pants? If an outfit consists of a shirt and pair of pants, then it is just 2 times 5. So you can have 10 outfits from the shirt and pants. And how many different ways can 3 people stand in a line? So say first people as name A, B, C. Then first of all, you can choose any one of them in the front line. So there are 3 choices to be standing on the first position. Then after this, there are only 2 possible choices happen for second position, right? Because already first position is filled up. So there are only possible 2 choices. And for the last position, because already 2 persons are chosen for each position, so there are only 1 possible choices for last one. So it is 3 times 2 times 1, which is 6, right? So it means that if you know how to use the fundamental theorem of counting, then you don't need to write down all possible choices like ABC, ACB, BAC, BCA, or something like that, right? So maybe this gives you some error because, however, if you know the fundamental theorem of counting, then you can just thinking it that there are 3 possible choices for first one, second one, and last one. So you have 6 possible cases, right? Okay. Great. And the next one, how does this relate to the number of Hamiltonian circuits in a complete graph with 3 vertices, right? So as we observed in here, observed in the example in the map, in case of the complete graph, Hamiltonian, all possible trees are Hamiltonian method, right? So in this case, what you can have is that actually the number of Hamiltonian passes are n factorial, and I want to explain what the n factorial means. So n factorial is just n times n minus 1 times n minus 2 times blah 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 2 times 1, right? So 1 factorial is just 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, and so on, right? So in case of Hamiltonian path, Hamiltonian circuit in the complete graph, for example, it's like just making people stand in a line, right? Because, for example, if you have A, B, C, D, on the Hamiltonian, on the complete graph, then maybe you can choose A, B, C, D. One of them will be on the first line, right? So there are four choices, four possible choices. And then the next choice is just three possible persons. And next one is two, and next one is one, right? But in this one gives you some possible words, including A, B, C, D, right? Using only ones, right? And any of these words, for example, if you just choose A, D, B, C, then it is represented as your path A, A, D, B, C. And since it's complete graph, you can go back to A without any difficulty, right? So it gives you Hamiltonian path, a Hamiltonian circuit. So any of the word consisting of those vertices gives you Hamiltonian circuit, right? And as you can see, there are n factorial ways to making people in standard line. So it means that there are n factorial Hamiltonian circuits in a complete graph. I know this is a repetitive part, so do you have any question on this? Oh, sorry. Yeah. Mm-hmm. Okay. Do you have any question? Okay. And there are n factorial over 2 Hamiltonian circuits in a complete graph if a circuit and its mirror image. Mirror images are, for example, mirror image of ADBC is just ACBD, right? So it's go back twice. So yeah, in case of mirror image, there are just n factorial over 2 Hamiltonian circuits. So, and if your starting point is specified, so if your starting point is specified, then there are n-1 factorial Hamiltonian circuits. Because starting point is fixed, for example, if you just pick A as a starting point, then all possible way is just standing the people B, C, D on a line, right? Because A is already fixed as a first one, right? And the last one, if you just do not count the mirror image as a separate circuit, then there are n-1 factorial over 2 Hamiltonian circuits, right? Okay. Does it make sense? So, yes, so quizzes will be take-home quiz, so you can solve it right now, or you can solve it in your home, right? Just solve it from now to 12 p.m., then that's okay, right? So thank you for listening to the lecture, and if you have any question, please let me know. Okay. And sorry for technical difficulties. Yeah. I always need to be familiar with this cutting edge room. No problem, thank you. Rainy, do we need to type our name for attendance or anything? No, if you just attend on the Zoom meeting, then Zoom will count your names in his server, so you don't need to type any name or anything else. Okay, thank you. Okay. Can you access? Oh, pardon, could you repeat again? From the record. So yeah, usually for chapter 1. Yeah. Yeah, I remember that you need to go on. Yeah. Oh, okay, got it. No problem. Yeah. So, yeah, if it is determined, please let me know. Then I will give you some makeup quiz or makeup test for you. Mhm. Mhm. Yes, it will be recorded and it will be uploaded. So maybe you can take the lecture, the recorded one. But for the quiz, also it will be take-home quiz. So maybe you can do quiz yourself. But please let me know if you need makeup quiz. Ah, sorry. I hope that you are. Yeah. Good. No problem. Thank you. Mhm. Mhm. So next quiz will be about the video quiz. So take, you mean the quiz one, right? Okay, sorry. Mhm. Mhm. Yeah. Yeah. Mhm. Uh, yeah. Actually, that's why the university do not require you to have Chromebook or any Chrome related thing because if you see the BYOD police, then they require to just issue a Mac, not the Chromebook because of that problem. So yes. Yeah. Yeah. Please let me know if you did one. Yeah. Do you catch? Mhm. So did you install the lockdown browser? Yeah, you need to install the lockdown browser. So could you? So yeah. So when go to is in your Mac? Okay, yeah. Go to Windows installation file. So and after downloading, yeah, you need to install it. And after downloading it, maybe you can just click this one to install everything, then go back to your page. So oh, then you can use launch it your browser to get. Okay. Thank you.
Today's lesson won't be on the page, correct? Or was
Yeah,
it?
today's lesson is not related to this. It is for chapter one. Thank you. Oh. Yes, yes. So I will wait for you. So you just take your time and if you let me know. Are you downloading it? Okay, got it. Oh, yes. So password for quiz today, I will send it. Give me a second. Yeah, HQ is midnight. So
But if we're here and it's too long, just feel free to tell us to get out. You know, the last thing I want to do is disturb your class. Yeah, I came in here and I was like, we've got to get pictures.